Albert Einstein, a name synonymous with genius, revolutionized our understanding of the universe. He wasn't satisfied with just refining old theories. He wanted to rebuild physics from the ground up. His general theory of relativity, presented in 1915, was a radical departure from Isaac Newton's ideas about gravity. Newton saw gravity as a force acting across space, pulling objects towards each other. Einstein, however, proposed a completely different view. He argued that gravity isn't a force at all. Instead, it's a consequence of the shape of spacetime itself. Imagine spacetime as a giant rubber sheet. Massive objects like stars and planets create dents in this sheet, much like a bowling ball placed on a trampoline. This warping of spacetime is what we experience as gravity. Imagine you roll a marble across our rubber sheet. If there's no bowling ball, the marble travels in a straight line. But introduce the bowling ball and the marble's path curves towards it. This is similar to how gravity affects objects in space. Planets don't just get pulled towards the sun by an invisible force. Instead, they follow the curves in spacetime created by the sun's mass. The Earth isn't falling into the sun because it's constantly moving, tracing a path through the warped spacetime around our star. Einstein's theory beautifully explained why Newton's laws didn't perfectly predict the orbit of Mercury, the closest planet to the Sun. Mercury's orbit is slightly elliptical, a deviation that puzzled scientists for centuries. General relativity accounted for this anomaly, proving that space-time warps more significantly closer to a massive object. One of the most intriguing aspects of general relativity is the equivalence principle. This principle states that the effects of gravity are indistinguishable from the effects of acceleration. To understand this, imagine you're in an elevator with no windows. If the elevator is standing still on Earth, you feel your weight pulling you down. Now imagine the elevator is far out in space, accelerating upwards at a rate of 9.8 meters per second squared, the same as Earth's gravity. You would feel the exact same downward force pressing you against the floor. Without a window to look out of, there's no experiment you could conduct within the elevator to tell whether you're experiencing gravity or acceleration. This profound insight forms the cornerstone of general relativity. One of the most dramatic predictions of general relativity is the bending of light by gravity. Because massive objects warp space-time, they don't just affect the paths of other objects, they also influence the trajectory of light itself. This bending of light has been observed during solar eclipses. Stars near the edge of the sun appear slightly shifted from their usual positions because their light is bent as it passes through the sun's warped spacetime. General relativity also predicts the existence of black holes, objects so dense that their gravity warps spacetime infinitely, trapping even light itself. These mind-boggling objects are still a subject of intense study today. Einstein's general theory of relativity wasn't just a new way of looking at gravity, it was a completely new way of understanding the universe. It showed us that space and time are not separate entities but are interwoven into a single fabric, space-time. His theory continues to shape our understanding of the cosmos, from the largest structures like galaxies and black holes, to the very nature of time itself.